Hello everyone. I hope all of you are doing well. I'm back again with another problem on particle kinetics. This is a very interesting problem in my opinion. Okay, so here is the problem. So first of all, I have the following system. I have a pendulum system. Okay, so let me draw a pendulum system with a fixed pivot here. So let's say that this is the location of the pivot. Okay, let me call this as the point O. Okay, I'm told that the pendulum starts off as a horizontal string. It is held this way here, and here is the bob of the pendulum. Okay, and then this pendulum is made to swing along a circular path. The length of the pendulum is L, the length of the string is L. This is the initial length of the string, and this is the initial position. Okay, initial position. Now obviously you know that this is going to travel along a circular path. I'm going to draw a circular path. Okay, so I just found out a nice trick in terms of drawing it. Let me do that very quickly. Okay, so this is an approximate circular path of the pendulum, let's say. Okay, let me get rid of some of these things. I don't need that here. I don't need that here either. So I'm going to just cut that out. Okay, so here is the bob of the pendulum. Let me color the bob a little more. Okay, so let's say that this is going to be of this color. All right, so here is the bob of the pendulum traveling along a circular path. Let me say that this path is made up of dotted lines here. Okay, this is the path of the pendulum. Now at some arbitrary angle theta measured from the vertical position. Okay, so let's say that the pendulum is somewhere here now. Okay, so after it crosses the vertical position at some arbitrary angle theta, okay, which I'm going to mark from vertical position. So starting from here, okay, so at some, and let's say that this is also a dotted line. So here is the angle theta. Okay, so this is the angle theta. So the first thing that I'm asked to do in this problem is that I'm starting from this initial position, and at this arbitrary position, obtain the equation of motion for the pendulum bob. Okay, so let's call the bob as the point P. Okay, so this is the point P. So the first thing is at some arbitrary theta, obtain the equation of motion, okay, of the pendulum system. Okay, this is something that we have done in the past, so we don't have any issues in doing this. So it's starting from this initial position. It is let go from rest. Okay, so the pendulum is let go from rest at the initial position. At its initial position. Okay, so this is the first part of the problem. Okay, the second part of the problem, okay, so this is a two-part question. Two-part problem. Let me underline that, just so that we are very clear that this is not just only an equation of motion problem. Now, okay, so part B of this problem is the more interesting part. So at some theta from the vertical, so this is the theta that is defined in the figure. So at some arbitrary theta, meaning so from measured from the vertical. Okay, so at some theta, the string of the pendulum is cut. Okay, then so what I have to do is the following. So determine the angle theta is equal to theta cut. Okay, or let me just call it as theta c. So at some theta is equal to theta c. Let's write it down here as well. Okay, so let me scoot this guy. Okay, so let me bring this guy here. So at some theta is equal to theta c, the string of the pendulum is cut. So determine the angle theta at theta c such that the pendulum, such that the bob of mass m is equal to 1 kilogram travels the maximum horizontal distance before it reaches the height it had at the time the string was cut. At the time the string was cut. Okay, so this is very interesting. I'm going to read this statement once again. Okay, so at some theta is equal to theta c, the string of the pendulum is cut. Determine the angle theta is equal to theta c such that the bob of mass m 1 kilogram, mass 1 kilogram, travels the maximum horizontal distance, okay, before it reaches the height it had at the time the string was cut. Okay, so how does this look in the form of a figure? I'm going to copy this figure from here. This so let's say this is the initial position, so I'll need everything from this figure, so I'll copy that and then I'll come back here and then I'll paste this guy here. Okay, so I'll say that, okay, this is the angle theta at which the angle the string is cut, so let me call this as theta c. Okay, going back here, so let's say this is theta at theta c. I'm going to cut off some of these things here, so I don't need this anymore. I don't need that anymore, so I'm going to cut that thing off. Okay, so at some theta is equal to theta c, this particle, the string is now cut. So what is the interesting thing that happens is that as the string is cut, right, this particle is going to do what? The particle is going to start moving as a projectile, as you can imagine. Okay, which means that, you know, it is now going to have some kind of a different path. Okay, so which means that the path of this is going to be the following. I'm not sure how that thing came here, but you know, I'm not interested in that. All right, so the path of the particle becomes a projectile now. Okay, so if I draw that out, it's going to look in the following manner. Okay, it's going to become a projectile. Okay, and let's put that in the dotted lines as well. Okay, and then you'll see that, okay, if I take this bob here, if I copy that and if I paste that, then at some point, you know, this bob is going to be traveling here. Likewise, it's going to be traveling here, and then at some point it will reach, let's say, this location here, okay, where it crosses this line that I'm going to be drawing now. Okay, let me draw that line in the red color. Okay, so this is the line at which it crosses at some point in time. Let me make sure that that indeed starts here. Okay, and what is special about this? This is the horizontal distance traveled by the particle before it reaches the height it had when the string was cut, right? This you can see very well from the figure. And so what we want to do is we want to find out this r. Okay, so let me call this variable as r. Okay, so find r. Okay, or find the theta. Okay, find the theta is equal to theta c such that this r is maximized. That is essentially what the problem is asking you to do. Okay, so the particle was traveling in the form of a pendulum right up till the point at which it was cut, and then after that, you know, this becomes a projectile path. Okay, and we want to find out the value of theta c such that r is equal to r maximum. Okay, so r has to be maximized. So how do we do that? And whenever you hear the word maxima or the minima, then you obviously know that, okay, hey, this is going to be involving some kind of a derivative. Okay, all right, so this is the second part of the problem. And let us now do the first part of the problem very carefully. Let us find the equation of motion at some arbitrary theta. Okay, so here is my solution. Okay, so solution. And that's a two-part problem, as I said. So the first part of the problem is, at some point, find out what the equation of motion is. Okay, so let me bring back my figure from before. Okay, these are fairly reasonable figures, I hope. So at some arbitrary theta, let us find the equation of motion in terms of theta. Okay, which means that when I'm going to do these things, I'm going to set up some coordinate frames, right? So what are my coordinate frames here? So I can set up a fixed observer at the point O. So this is a fixed point O, and then starting from the fixed point, I can look at the particle P at some arbitrary theta. But here is what I want to do first. I'm going to call this angle here, okay, this entire angle here, as the angle phi, because the angle phi is measured from the initial position. Okay, so angle phi is measured from the initial position. Okay, which means that at some arbitrary theta, what is the relationship between theta and phi? Okay, are they related in some way or the other? That's something that we need to know. And that's fairly from basic geometry. You can see that phi is 90 degrees plus theta. Okay, at some arbitrary theta, phi is equal to pi by 2 plus theta. Okay, so this is the relationship between the two. Phi is a function of time, theta is a function of time. Both of them are functions of time, which means that we also have the following. So we also have that if I differentiate both sides with respect to time, d phi by dt is d by dt of pi by 2 plus theta, which means that pi by 2 is a constant. So phi dot, that did not come out too well. So phi dot is equal to theta dot, which also implies that phi double dot is equal to theta double dot. So these are important pieces of information, so I'm going to underline that here, and then I'm going to have this guy here as well. Okay, so that is important. Then what do? I set up a unit vector frame. Okay, so here is the thing, and I'm thinking my figure will still come out if I do it. Yeah, it still did. Very nice. Okay, so I'm going to set up a coordinate frame here. This is the angle phi as I'm measuring. Okay, which means that I'm going to be setting up a unit vector system in the direction of the particle P, and this is going to be the E suffix R direction. Okay, this is the length of the pendulum, which is a fixed length L, and then E phi is going to be in the direction of increasing phi. Okay, so this is going to be the direction of increasing phi tangent to the path. Okay, that is important to know as well, right? So this is going to be tangent to the path, and this is going to be E phi. Okay, and it's very simple to see that the number of configuration coordinates is 2, number of constraints is 1, so the degree of freedom is theta or phi here. Okay, so let me just maybe quickly write that out. Okay, so check to see the number of configuration coordinates is equal to 2, the number of constraints is equal to 1, which means that the number of degrees of freedom is equal to 2 minus 1, which is equal to 1. So theta or phi is our degree of freedom, as you can imagine. Okay, this is something that we've been doing for most of the problems, and I'll try to solve a problem where there are 2 degrees of freedom very soon. Okay, all right, so this is the situation that we have. Now what do? I have to set up the position vector and so on. So here I have the length L. Okay, so I can say that the position R P slash O is equal to L times ER. Okay, and then I can say, okay, the velocity P slash O is I'm going to skip the details of these because we have done this in the other problems. Okay, so the velocity is going to be L times phi dot E phi, where we are making use of the fact that when you're doing the time derivatives, der by dt is phi dot E phi, and dE phi by dt is minus phi dot ER. Okay, so that's essentially what I've done to calculate the velocity. And then when I do the acceleration, so maybe let me do these things a little more carefully, because perhaps it might be useful to some. So this is the position vector, so let me cut that off and then say, okay, start from the beginning. Velocity p slash o is d by dt of L ER, which is dl by dt ER plus L der by dt. But dl by dt is 0, right, because it's a constant, which means that I can go back and say, okay, velocity of p slash o is L phi dot E phi. So that is essentially what I've done. I've substituted for der by dt, and we know that der by dt is phi dot E phi. Okay, and then if I do the acceleration, p slash o, this is going to be d by dt of L phi dot E phi. So this is going to be, L is a constant, so I'm not going to do the differentiation for that. So this is going to be L d by dt of phi dot E phi, and then L phi dot times dE phi by dt. Okay, which means that the acceleration of p slash o is going to end up having the following form. Okay, so this is going to be minus L phi dot square ER, where I substituted for dE phi by dt, and then this is going to be L phi double dot E phi, where we have said that dE phi by dt is minus phi dot ER. So this is something that you should be expected to know how to do, typically in an exam or so on. This information will not be given to you. You might be asked to do this. Okay, and I can write this in terms of theta as well, right, because I know. Okay, so I'm sorry, I need my regular color, so can also express in terms of theta. Okay, we know that phi is pi by 2 plus theta. We also know that phi dot is equal to theta dot, and phi double dot is equal to theta double dot. Okay, so which essentially tells me that R p slash o is L ER, then V p slash o is L phi dot, which is the same as L theta dot, but E phi, and then A p slash o is going to be minus L theta dot square ER, and then L theta double dot E phi. Okay, so these are the things that we know. I'm just going to group them together. Okay, so this is important stuff. And you also obviously know that this is going to be acceleration in the radial direction, acceleration in the phi direction. So AR is going to be minus L phi dot square. A phi is going to be L phi double dot. Okay, then what do I do after this? I come back, and if I have to do my equation of motion, I have to draw the free body and the kinetic diagram. Okay, so draw the free body and the kinetic diagram, and then perform force balance. Let me see if I have enough space for that. Yeah, I think I do. All right, so I'm going to go back and bring my figure here. Okay, so let me take this creature and copy that and bring that down here. I can draw the free body and the kinetic diagrams. So let me do that. Okay, so let me take all of these, and my hope is I might be able to get rid of some of these things. Okay, so I'll cut that off. I don't need to cut that off, I'll keep that. Okay, so I'll just reduce the size of that, and I'm going to copy this again so as to write out my kinetic diagram, and I'm going to bring these two guys slightly down and spread this out and spread this out. Okay, beautiful. And this has to be a little straight. Okay, I don't need that here. Okay, what are my forces in the free body and the kinetic diagram? This is the particle P, so I know that. don't need that, that's a distraction. And so here are my ER and E phi directions on the kinetic diagram. On the kinetic diagram, it's very easy: mass times acceleration, mass times acceleration. Okay, so that's essentially what you have. So this is going to be m times a phi, and then if I can twist my hand here and write out, this is going to be m times AR. Okay, so this is going to be the kinetic diagram. And then I have my free body diagram. Once in a while, I still try to do these things well, but they don't come out too great. Okay, I have my free body diagram. I'll go back here. I don't know if you get irritated by my jokes or something, but I'm trying to keep it a little light. I know dynamics is heavy. Okay, all right. So here are my forces. I first have the tension. Okay, which is why I had that little bit of string sticking in there. And then I have these forces, the weight of the bob, which is acting vertically down. Okay, so this is going to be acting vertically down. So this is m times g. Then you can figure out that this angle here is going to be the angle theta. So I'm going to break it into components in the E phi direction and then the ER direction. Okay, so here are the components, and I'm going to make sure that that is indeed in the ER direction. Okay, so this is going to be mg times cosine theta, mg times sine theta. Okay, so these are the components. So free body diagram is done, kinetic diagram is done. Let us now do the force balance. Okay, so sum of forces in the radial direction on the free body diagram, things pointing in the positive radial direction, this is equal to sum of forces in the radial direction on the kinetic diagram, things pointing in the positive radial direction. What are the forces? Okay, so in the radial direction, I'm going to have mg cos theta minus the tangent t. This is equal to m times AR. That's equation 1. Then likewise, sum of forces in the transverse direction on the free body diagram is equal to sum of forces in the transverse direction on the kinetic diagram. Positive transverse direction, positive transverse direction. What are my forces? I'm going to have minus mg sine theta. This is equal to m times a phi, as you can see from the kinetic diagram. Okay, so this is equation 2. Now I'm typically interested only in the equation of motion. Let me simplify both the equations. Okay, so simplifying. So from equation 1 and then substituting for AR, okay, which was minus L theta dot square as well. So I'm going to have T is equal to mg cos theta plus ml theta dot square. Okay, this is the constraint equation. Okay, so this is the constraint equation. And then I'm going to have from equation 2, I guess, substituting a phi as L theta double dot, I'm going to have the following. The mass is going to cancel off on both sides, so I can get rid of these two creatures. I'm going to have, I guess, go back to my regular color. So theta double dot is going to be minus g by L sine theta, and this is going to be my equation of motion. Alright, so I'm done with the first part of the problem. Okay, this is hopefully not much of a sweat. This is something that we've been doing for some time now. Okay, alright, so this is the equation of motion. Now I come back to the second part of the problem. Okay, so this is the more important part of the problem. Okay, now go to part 2 of the problem. Now we shall go to the second part of the problem. Hooray! All right. Going back to my figure here, I had a nice figure. Oh yes, this guy here. Okay, so this is the figure that I had that I want. All right, why is this Not selecting. All right, it's going to select in a minute. Okay, so I'm going to bring back that figure here. Okay, so these are the events that are taking place when the string is cut. Okay. All right, so how do I go to tackle this part of the problem? Okay, so I just want to underline it here. Okay, one thing I want to mention is this. Okay, so since no mention of drag, we do not need to use drag when looking at the bob as a projectile. Okay, I hope that makes sense. The important thing that I want to mark in this figure are the following. Okay, right as the bob gets cut, it's going to have a certain velocity. Okay, so this is let me say that, okay, this is the direction of the velocity as the bob gets cut. Okay, so let's say that, okay, this is velocity c. So vc, let me say, so vc is the velocity of the bob at the time the string is cut. Okay, which means that vc is typically the velocity at theta is equal to theta c, and so vc is equal to L times theta dot c. Okay, because we previously knew, if you go back and look at your kinematics here, you know that the velocity is L theta dot, which means that at the point at which it is cut, it is going to be theta dot c. Okay, where theta dot c, so here theta dot c is the angular rate at theta is equal to theta c. So that's one thing that we know. Okay, and then we know that, okay, this projectile is going to be traveling in the form of a particle which is only under the action of gravity. Okay, so that is one thing that I also know. So which essentially means that can I find some angles before I go on and do other things? I can do that very quickly. Let me show you here. Okay, let me bring this. Okay, so you see this angle here at the point at which it is cut, the angle between VC and the string, which is having a length L, is going to be an angle of 90 degrees, which means that it can be easily seen that this angle here is going to be theta c. Okay, so which essentially tells me that when I'm looking at the location where the string is cut, the velocity is in terms of theta dot c, and the angle, the initial launch angle of the projectile is now theta c. Okay, so I'm going to maybe take this figure once again. Okay, and I'm going to maybe clean up some of these things and look at it only as it travels as a projectile. Okay, so let me do that now. So let me bring that down here. So bring the same figure down here. So we see that for the projectile, so as string is cut, the bob becomes a projectile with an initial launch angle of theta is equal to theta c and an initial velocity vc is L theta dot c. Okay, and you can obviously see that if I take this velocity, which is vc here, okay, so this is vc, which is L times theta dot c. I can split it up into components along the horizontal and the vertical, which is what I'm going to be doing. Okay, this angle here is theta c. So these are the components. Okay, so this is going to be vc cos theta c, vc sine theta c. Okay, so I'm going to say that these are the x and y components of the velocity of the projectile at the launch point. Okay, so I'm going to say Vx naught is equal to Vc cos theta c. Vy naught is Vc sine theta c, where Vx naught and Vy naught are the components of Vc at the initial launch of the projectile. Okay, I hope that makes sense. And if I do the following now, okay, so I'm going to take this figure. I had this from before, so I'm going to cut off some unnecessary aspects of this figure, and you'll see what I'm talking about soon. Okay, so I'm going to get rid of some of these things, not all of that, but some of these things, as you will see. Okay, and let me cut this piece off. Okay, so I'm going to just cut that off. Maybe I can clean up a little more. Okay, now I see that, okay, this is similar to projectile motion essentially, right? So I'm going to say, okay, this is my y-axis, okay, and this is my x-axis. Okay, and if this is my x and y axis, then I can essentially say, okay, I have projectile motion equations which I can use from before. Okay, so using the standard projectile motion kinematic equations. Okay, that is something that we have seen in the past. Okay, so I'm not going to go ahead and derive it. It is not necessary unless I ask you to derive it. It is not necessary. Okay, but you can very well easily derive it. It's not a big deal. I mean, you can see that if you wanted to start the derivation, then you would have probably said, okay, acceleration is 0I gj, which means that ax is equal to 0, so this is dvx by dt. Ay is equal to minus g, which is dvy by dt, and then if I do the integrations and so on, I get vx is equal to vx naught, and then from here vy is vy naught minus g times t minus t naught, and etc. etc. So this is just a sample derivation. Okay, expect to know how to do these things. Okay, so please expect. Okay, so please expect to know how to derive the projectile motion equations in with drag and without drag. Okay, so both with and without drag. Okay, this is just as an aside for us. Okay, this is something that you need to know. All right, so I have all of these. So from basic projectile motion equations, no drag. Okay, and I'm going to say, okay, hey, x naught is 0, y naught is 0, then t naught is also 0. Okay, and here are my equations, and then this is at the initial location. So at t is equal to some tf or something, okay, my x value is equal to the range r, which I need to maximize, so I don't know, well, the y value is going to go back to 0, right, as you know from before. Okay, because that is essentially what is going on here. Okay, so this is at that particular position. This is at t is equal to t naught. Okay, and so I have all of these. Now I'm just going to go back and look at my projectile motion equations. So what are the equations? I have vx is equal to vx naught, which is going to be vc times cosine theta c, so that vx is going to be L theta dot c cosine theta c. Then vy is vy naught minus g times t minus t naught. If I do the substitutions, vy is going to be L theta dot c sine theta c minus g times t. Okay, then I'm going to have x is equal to x naught plus vx naught times t minus t naught. which means that x is equal to x naught is gone, so this is going to be L theta dot C cosine theta C times time t. Okay, then lastly I'm going to have y is y naught vy naught. This is supposed to be an x here. I'm sorry if that doesn't look like one. This is vx naught vy naught t minus t naught half g t minus t naught square, so that y will become the following. So this is going to be L theta dot C sine theta C times t minus half g d square. Okay, so these are all the standard equations which I have manipulated for the terms of our problem, okay, or the terms and conditions of our problem. Okay, now, all right, I don't want that color. All right, I guess I did want it here for that, and suddenly these things disappear. Okay, so now at t is equal to tf, x is equal to r. Okay, so I'm just going to look at substituting r into the equation that I have, and then y is also equal to 0. So if I do the substitutions, this tells me that, okay, r is equal to L theta dot C cos theta C times t. Okay, so that's one thing. And then I also know that 0 is equal to L theta dot C sine theta C times t minus half g d square, which means I can substitute for t, right, in terms of theta dot C right there, and in terms of theta C as well, right? So I can do all these kinds of things here. Okay, so which essentially tells me that t is equal to, so solving from this is from the x equation, and this is from the y equation, which essentially tells me the t, if I cancel off these factors and so on, so this is going to be 2 times L theta dot C sine theta C divided by g. Okay, which means that substituting for t into the range equation. What is the range equation? This is the range equation. Okay, what do I get? I end up getting the following. So r is equal to L times theta dot C cosine theta C times time, which is 2 times L times theta dot C sine theta C divided by the acceleration due to gravity g. Okay, or I can get the following. R is equal to 2L square, okay, theta dot C square cosine theta C sine theta C, all of this divided by g. All right, so far so good. I mean, we are on the right track. But the question is this, the question, how to write theta dot C in terms of theta C? What do I do? For this, I revisit my equation of motion. Okay, so revisit equation of motion. Okay, so from the equation of motion, this was in the first part of the problem. Okay, we know that theta double dot is equal to minus g by L times sine theta. Okay, so what do? I have to use the chain rule. Okay, so use the chain rule. Okay, theta double dot, we know from the chain rule is going to be theta dot d theta dot by d theta. Okay, we have done this before, so I'm not going to go over this again. Okay, so this is the chain rules. If I underline some of these things, so from equation of motion in the first part of the problem, Okay, this is what we had. Then I'll go back to my regular color, so which tells me that theta dot d theta dot by d theta is minus g by L sine theta, which means I'm going to now do the integrations after cross multiplying. So this is theta dot d theta dot is equal to minus g by L sine theta d theta. Look at my integrals. Okay, this is going to start from theta dot naught to theta dot cut. Let me write that properly. To theta dot cut, which means that this is going to go all the way from theta naught to theta cut. Okay. Question is, what is theta dot naught and theta naught? Okay, so look at initial figure. If I scoot back up, okay, very quickly, while making you dizzy, you can see that at the initial position, when the string was completely horizontal, okay, what would be the value of theta c? Okay, so this is something that you want to be very careful about. In sense, initially the position of theta c, if I use a different color here, okay, the initial position of theta c is going to be measured negative. Okay, so this is going to be theta naught, which is minus pi by 2, because the pendulum is swinging the other way, right? Which means, so if I'm measuring theta naught this way, it's going to be negative. Okay, so which means that theta naught is negative, but then initially everything starts from rest, right? Which means that theta dot is going to be 0. Okay, so at this position, theta dot naught, let me write that properly. So theta dot naught is equal to 0 at the initial position. Okay, so that is something that we know. So if I go back to my problem here, then I know that, okay, by looking at the initial figure, theta dot naught is equal to 0 and theta naught is equal to minus pi by 2. If I do the integration, so this is going to be theta dot square by 2 from initial limit of theta dot naught is equal to 0 to theta dot c, and this is going to be g by L. Integral of sine theta is minus cos theta, so this is cosine theta from minus pi by 2 to theta cut. If I do the cleanup of all of these things, I end up getting the following. Okay, so theta dot square cut is equal to 2g by L times cosine theta cut. This is really nice. Okay, so we are almost done. Now I'm going to take this and substitute into the R equation. Okay, what is the R equation? That is the equation that we had here. I'm going to bring this guy here, so copy that, and then I'm going to bring that here. So this is the R equation, which is this guy. So that is the range equation. So if I do the substitutions, I end up getting the following. So R is equal to 2 times L square. Okay, so that's essentially going to be 2 times L square, and multiply by theta dot square c, which is going to be 2g by L. So that's going to be 2g by L. Okay, and then this is going to be cosine square theta c sine theta c divided by a factor of g. Okay, and so let me assume that the string length is equal to 1. Let us assume that L is equal to 1. Okay, say, not necessary, but we can. I'll cancel off some common terms. Again, bad habits, I keep going back to my palette there. So that's gone, g is gone, g is gone, and so I end up with the following. Okay, so I have essentially R is equal to 4 times L times cos square theta c sine theta c, and so if I say L is equal to 1, this is 4 times cos square theta c sine theta c. Okay, now for R to be a maximum, to find theta c at which R is a maximum, what do we need to do? we need to do the following. We need to say dr by d theta c is equal to 0, which means that d by d theta c of 4 cos square theta c sine theta c is equal to 0. If I do the differentiation, I'm going to end up having the following. The factor of 4 is going to knock off, okay? So this is essentially going to be differentiation of cos square theta sine theta c. So that's going to be cos cube theta c. Okay, that's one thing. And then minus 2 cos theta c sine square theta c. That's equal to 0, okay? Which implies that if I can get rid of some of these common quantities, then I can say that, okay, cos theta c is equal to 2 times sine theta c, okay? Cos square theta c is equal to 2 times sine square theta c, which essentially tells me that tan square theta c is equal to a factor of half, which means that tan theta c is 1 by root 2, which tells me that theta c, the angle at which I need to cut, is approximately 35.3 degrees. So at this angle, R is R max. Okay, so that is the end of this problem. It's a very nice problem. Once again, if I quickly go back to what the problem was, okay, so here was a problem. Maybe this is a better figure. Okay, so initially it was at this position, it was let go from rest, it performs simple harmonic motion, which you will see when you talk about vibrations later on. Okay, it just keeps rocking back and forth, right? So as it comes and goes past the vertical position, somebody snaps off the string, and then as they snap off the string, right, so as they cut off the string here, it becomes a projectile. You are asked in the first part of the problem to come up with the equation of motion, which we have done here. Okay, then in the second part of the problem, you're asked to find out, okay, what is the value of theta at which it is cut such that R is maximized. And that is exactly what we've done by making use of basic projectile motion equations and then going forth and obtaining what this maximum value of R max is at theta c. Okay, so I hope this makes sense to everybody, and this is a really nice problem. I hope you look at it very carefully. Okay, all right, thank you very much, and take care of yourselves. Here is the final answer if you want to take a look at the final answer. Okay, all the steps that we've gone through. All right, thank you, and take care. Bye bye.